Hello, Mr. Thomas.
Hello, dude. How you doing? You
Hello,
well?
good morning.
Good morning, mister. How are you?
I'm too good. I'm too good.
I answered the assignment you gave us yesterday.
Yes. Did you upload your answers as well?
Yeah.
Let me show you what I can see.
See,
I'm
see,
just-
my-
I got the answers, but I don't know how to upload.
let me show you what I can see. So I'm going to share my screen. By the way, we are live streaming to YouTube now. So if you say anything ridiculous, you'll be remembered for all of posterity. As soon as you say something.
Good morning, Mr. Thomas.
Hey, good morning. As soon as you say anything ridiculous, I will just mention you by name and say where your family lives, and then you'll be live on YouTube. Right. Anyway, let's go to the Google Classroom where I'll show you what I can see. I asked people to upload stuff, and yesterday all I'd got was Zaid's answer. So let's have a look. Student work.
Also me, Mr. Yesterday.
Yeah.
Check again, please.
Well, I'm checking now, but so I can see. Oh yeah. Okay.
Yesterday, I sent it upload yesterday.
Brilliant. Okay.
Really?
Well, what time yesterday? It wasn't in the lesson, was it?
No, not in lesson, Mr. After the lesson.
Oh, because I set enough work so you could do it just in that lesson. And so I checked at the end of the lesson to see, and it was only
Because,
Zaid.
Mr. Yesterday, I can't join in your lesson. I don't know. Maybe you didn't accept me.
Maybe, okay. All right. All right, excellent. So let's have a look. If I click on this, can you see my screen?
Yeah, we can see.
Yes, sir.
Okay.
Oh, this is my answer.
Yeah, these are you. Okay, this is good. 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 This is correct. This is all correct. Well done. 10 out of 10. Excellent.
Because I see the video, Mr. Then I answer the question.
Well done. So that was Abdullah Fahad Al-Dasari. Okay, so Abdul Rahman, should we have a look at yours?
Yeah, see my.
Displacement, this is correct. All right. Oops, whoa, sorry. So this is good, this is good, this is good. This is correct. This is all correct. Did you all do this together?
This I do with the video, Mr. I see the video, then I answer.
Brilliant. This is excellent. Hamad.
The video helped me, Mr.
Okay, Hamad, let's have a look at yours.
I think I got 7, mister.
Because it measures the length of the body in motion. Yes, that's right. The trick with this one is time. Some people think time has a direction because people think, well, maybe time is moving forwards. But the question to ask yourself is, do you need two numbers to adequately describe a time? No, you don't. You just actually need the time. So that's why displacement is the only one that's correct. You got that right. Small. This is right. This is right. This is wrong, because what you've done here, if you look at this, the work that you've done is on the top, which is 90 newtons times 10 meters. Okay, 90 newtons times 10 meters is what you've done. And then the useful output is working against gravity, 200 newtons times 4 meters. That's the useful output. So you've got it the wrong way around. So actually you want the useful output. So you've got the equation the right way around, but the useful output is 200 times 4. Well, 200 newtons times 4 meters, of course. And the total input, the total effort that you did was the 90 newtons times 10 meters. For Newton's third law, forces act on the same objects. Well, that's not true. Sorry. Newton's third law, the same force acts on different objects. So different objects is true. You were asked to say which is not correct. Which is not correct.
Okay, Mister. I thought because it was correct, I thought I
Yeah.
needed to explain.
It's not correct. So the only one that's not correct is that the forces act in the same direction. They act in opposite.
Second one.
Yeah. The forces act in opposite directions. That's right. Okay. A ball is thrown vertically upwards. This one is correct. It's always 9.81. Zaid, if you're on the call, let's have a look to see if where's Zaid, my friend here. I've got to admit. Some of them are late. Okay, you guys are late. I don't know why you're late. There's no reason for it. You don't even have to travel. You can just basically rock up onto your
Mister,
computer.
there is a problem. Now I come here.
Really? Okay.
Yes.
Well, let me just check to see if we've got everybody. MA, who's MA? MA, welcome. Who is MA? Can you put your full names in on your Zoom? Otherwise, I won't know who you are. Mr. MA, maybe put your full name in. Anyway, let's have a look at this one. This is correct. 7 is correct. 8 is wrong. The reason why 8 is wrong is because, will you tell me why is, okay, Abdul Rahman, if you're listening, why is 8 wrong?
Because this graph acceleration, Mister.
Yep. Well, this is showing you the potential energy. Now, potential energy, the formula for potential energy, we know that.
Graph for potential energy. Sorry.
Potential energy, right? Let me draw on this.
Mass, gravity, and
Correct, exactly. So potential energy is mgh. Now, is m changing? Does the mass of the ball change?
No, doesn't change. Doesn't change.
So basically, we can ignore the m because that's not changing. Does g, the acceleration due to gravity, change?
No.
No. So the only thing that's changing is height. So a graph of time against potential energy is really the same as a graph of height against time, right? It's the same thing because basically this is mg, which is constant, times h. So you've got to say is, when you drop something, does the height change in the straight line?
No.
That would mean that the distance height change in height divided by the change of time is constant. And that would mean that would mean it's a constant velocity.
Yeah.
Now, I don't think it was a constant velocity because when you drop something, it will accelerate. So this is what happens if you've got an increasing. If you think about this,
if you want to draw a graph for accelerate, it will be same as the curve.
This, if you look at this, that's right. This region, the delta H, and then the delta T, that gives you the gradient. So it gives you the velocity.
Yeah, then you can see how many accelerate the graph in 1 second.
And then this region, delta H is much more, and delta time is less. So this has got a greater velocity, and that's what you'd expect if it's accelerating. Okay. So it's this one, right? Let's have a look. Whoops. Let's have a look at number 9. This is just a definition, this one, isn't it? Let's go back to discard changes. That's fine. Let's go back to your question, your paper, Hamad. You got this one right. Yeah. Young's modulus is a general thing which applies to a type of material, and the stiffness is applying to the material turned into a particular object. This is right. Okay, nice one. You got that right. Well done. This last one, I think we had this in mock. We had this in mock 2.
Yes, we did.
So I think I'm surprised that you didn't get that one right. You should be able to ignore these 2 right
because,
away.
Mister, when you explained in the video, I couldn't gather information, Mister, to calculate. I didn't.
Didn't I not give you enough hints?
Yes.
Okay.
Or in the class, we didn't get this question in class.
Okay, Do you want me to explain this one now? I think,
Yeah. Explain.
is it
Yes,
worth me
yes,
doing
please.
this?
Explain,
Okay.
Mr.
Right, let me do this. I'll go to here and I'll do it on this and then we'll have the actual full explanation. Right, so I'm going to go this step by step, nice and slowly. So let's make sure we understand the question. A student used a balance to measure the mass of a small cube. This is a small cube with sides of length x. So if it's a cube, if this is x, then this is x, and then this is x, right? So the volume of the cube is x cubed. Do you agree with that, everybody?
Yes.
Yeah. So the density, which is equal to mass over volume, is equal to 50 grams divided by x cubed. Now, the reason we don't need to actually work out what it is because we have the new cube length in terms of x. So we don't even have to work out what it is. But sometimes you might want to. If you like doing calculations, what I would do in a question like this, if you liked using your calculator, just let x equal 1 meter. Right? And then you can have actual numbers that you can work out. The density of the small cube then is 50 grams divided by 1 meter cubed, which is equal to 50 grams per meter cubed, right? And that gives you a number. I'm not suggesting this is the best way to do it. I think you should do it without numbers. But if you like numbers, I know some of you boys love numbers, so actually use real numbers. And if we then had, if x was 1 meter, and we now have a larger cube of 1.5x, that means it's 1.5 meters times 1.5 meters times and the height 1.5 meters. So now I just use 15 cubed as a way of sort of working it out because in my head I can work that out. But if you want to use a calculator, just do 1.5 times 1.5 times 1.5. And what does that give you on your calculator? You can actually do this.
Calculator, Mr. Just a minute.
Do on your computer or actually on your, you can do it on your phone, you know.
3.375.
Right, so that should give you something like 3.375. Now, if we've done it in meters, then this will be meters cubed. And then we could work out the mass is the same. So the density of the larger cubed is equal to the mass divided by the volume, which is equal to, again, 50 grams divided by 3.375 meters cubed. And we get a number for that, right? But you notice, if you look at this carefully, this is 50 grams per meter cubed.
The mass,
yeah.
50 grams for the down one.
The mass is still the same, yeah? Because look, it says 50 grams.
Yeah, yeah.
So the mass is the same. So the density of the first one is 50 grams per meter cubed, and the density of the second one, let's just do the actual maths. If we want to, we do 50 grams divided by 3.375 equals, and this is going to be equal to 14.8 grams per meter cubed. So density of the small one equals 50 grams per meter cubed. Density of the large one, we just worked it out, equals 14.8 grams per meter cubed. So what's the difference? Well, the density of the large one is equal to about a third. You should be able to see that it's about this one, 0.3 times the density of the small one. Now, you don't have to work out any calculations at all, because you could just leave it all in terms of x if you want to as well.
How, Mr. did we get D?
Yes, how, Mr.
How do you get D?
Yes.
Okay. Do you follow me up to here?
Yes, here.
Up to there?
Did you divide or what did you do?
Okay. Right, good question. very, very good question. Right. So all I did there is I said, well,
you do the bigger cubic divide by the small cubic, yeah? Cube.
Watch this. Look at this. If I rearrange this equation, I have density of large divided by density of the small one equals 0.30. Do you agree with that?
Yes, but you
Yeah?
you didn't know the answer before you.
No. Correct. I'm just saying. But if you do this, okay, yeah, I'm just showing you how to work from there. If you don't know the answer, but you always know the answer in a multiple choice, you know it's one of them. But if you don't know the answer, then what you could do is just say, I've got to look at the format. I've got to look at the type of answer. And I've got to say, well, it's got to be one of these. And each one of these, you've got the large one is equal to something, some magic thing times the small one. So you've got to find what this ratio is. And then the way you find that is just saying, okay, well, this ratio, this number is equal to the larger one divided by the smaller one. Well, I have the larger one. I have the larger one over here. The larger one is 50 grams per meter cubed, and the smaller one is 14.8.
No,
So
Mister.
No, the
Yeah?
opposite, Mister.
No,
Different.
wrong.
The opposite, Mister. 14 is the large one.
Sorry.
large one
Yeah, sorry.
0.85.
Sorry. No, you're right. I've just written them the wrong way around. Yeah.
You make
Correct.
a big, massive wrong, Mister.
Yeah. The large one, the density of the large one is, of course, less. Of course it is. Divided by 50.
It will be, Mister, 0.297.
296.
About, yeah.
Yeah, about this.
About that.
You
But you don't need to do any calculations. The best way to answer this one is to look at the answers. You know that the density of the large one is going to be less than the small one. You know that because it's the same maths. So you can cross out those two right away. And then you know what the density of the large one, about how many times? Well, it's going to be about 3 times smaller because the volume is about 3 times bigger. Yeah. So
yes, that's correct.
You've only got 2 choices. You've only got one. This one, the density of the large one is 0.3 times the small one. And the other option, this is D. And the other option that it could be, C, the density of the large one is 0.67 times. So it's like 2/3. Well, you know it can't be that one because that doesn't work with the volume being 3 times bigger. So I'm just thinking that because you've only got a minute to do each question, you don't really want to be doing lots of calculations. You want to be looking for a shortcut.
No, but Mister, basically, we put instead of X a number, like 1, right?
If you want to do it with numbers, the easiest way to do it is choose a very easy number, like 1. Yeah, of course.
And then, how do we know that it's not 0.67? Because we ruled out A and B because they are too big.
Yeah.
So how
Correct.
do we?
And you rule out C because C is there's too similar. Because how much has the volume changed? The volume of this one is 1 meter. So it's 1 times 1 times 1 in meters, which is equal to 1 meter cubed. And the only difference, the mass isn't different. So you look at the volume of the other one, and it's 1.5 meters times 1.5 meters times 1.5 meters. So the volume of the bigger one is 3.375 meters. So the only difference is instead of a volume of 1 meter cubed, you've got a volume which is 3 times bigger. So the mass hasn't changed. So that means the density of the large one is going to be 3 times smaller. And 0.3 is about 3 times, well, it means it's kind of like divided by 3, isn't it? Pretty much. Is that too tricky?
Oh, Mr. Easy.
I don't think it's too bad. I think this one was quite hard. I think the hardest question is this one for sure. Question 8, because you've got to think about it. In general, you hardly ever see straight lines in physics.
Straight line. If
Yes.
you will draw for acceleration, it will be a curve.
You will see a straight line when you're looking at velocity time graph if there's no air resistance, because the acceleration is the gradient, the velocity time graph, and then the acceleration will be steady. But most of the time, whenever you have a change of position, change of distance,
That's mean Mr. Displacement, the C and B, yeah?
Displacement. Yeah, most of the time when you drop things, you're talking about their energy or their displacement, potential energy, kinetic energy, displacement. Most of these are curves.
Yes.
Yep. What's the question?
No,
So,
just
Mr.
Okay.
Vectors have a curve if they were put in a graph, and scalars have a straight line.
No, it's not quite as simple as that. I'm just saying that in general, you don't often get straight lines. So if you don't know, if you have to guess, most of the time you'll guess for a curved line because that's more normal. You do have, I'm just saying if you don't know the physics, if you can't work it out, you don't often see straight lines. The only time you typically see a straight line is something like this, which is when you've got a velocity time graph. Now this will be a straight line when the change in velocity over the change in the time, the gradient of that is constant. And this will happen when you're dropping something. So dropping something under gravity and you're ignoring air resistance, you'll get a straight line. When you ignore air resistance, often they will tell you when to ignore air resistance. But of course, it won't go this way around, actually. It'll go this way around, won't it? Because the velocity will be negative, usually, and it will start off something like this is what's going on here. Hang on a sec. Let me draw this a bit more accurately. Okay. So I'm going to make that a little bit shorter. This is time, and this is velocity.
For Mr. Calculate the acceleration, yeah?
I'm just asking you what's happening. Tell me what's happening in this.
Because it's falling, the velocity decreases.
Hang on a second. Hang
The
on a
velocity
second.
increases until it stops.
يا ولد
At t equals 0. At t equals 0, does it have velocity?
This
doesn't have.
Displacement, Mr.
I'm asking you, I'm just asking you a question now. Look at this diagram. Tell me as much as you can about what's going on. Velocity is up here. At time equals 0, there is a number.
There is a number, yes.
Yeah. So what's happening? That means it's got an initial velocity. Right? It's got an initial velocity.
Correct.
After a certain amount of time, say t1, what's its velocity now?
0.
Right. Excellent. 0 velocity. And after a certain amount of time at t2, what's it got now?
Final velocity.
Minus.
Well, it's got a velocity. We can call it a final velocity if you like, but it's got a velocity, and this velocity is
negative,
approximately equal to the initial velocity.
Mr. If the velocity negative, it will be displacement or normal velocity.
I want you to look at this. Good question, and tell me what is happening in real life in this example.
That means he go to place, then return back to first place.
Okay, that's not completely wrong, but I want you to be able to describe the motion of it. So I want you to think, first of all, first of all, question, is the gradient changing?
No.
No.
So what does that mean?
Constant velocity.
No,
Constant velocity, yes.
no, not constant velocity.
Come on, bro.
Acceleration.
Constant accelerate.
Gradient is the change in y over the change in x. What is the change in y? Change in velocity. And the change in x is the change in time, right? So
Distance.
this is constant. So what is constant?
Mr. Distance.
Acceleration.
Acceleration. So this is a constant acceleration. So
We
I
said
told you
acceleration, Mr.
constant acceleration.
I said acceleration.
correct. Constant acceleration. Excellent. So it's a constant acceleration. So it could be ignoring air resistance, but we have an initial velocity equal to plus v. And then we have zero velocity after a certain time. And then we have a velocity equal to about minus v in the end. So what's going on? Explain to me what's happening in real life. If you watch this, what would be going on?
Mr. Something is dropped and then bounces back, or the opposite.
Close, close, but not dropped. Because if it was dropped, it would have no
Thrown up,
initial
thrown up,
velocity.
Mr. Thrown up.
Excellent. Something is thrown up. So a ball or something is thrown up. It's released there. Then it gets here. What's happening here at T1? Maximum
hand.
height.
Maximum.
Maximum height because it's zero velocity. It reaches the top. And then what's happening in this part?
Comes back.
It's coming back down. So if you were looking at distance, and distance is the area under the graph, it's moved a certain distance up, and then it's moved a certain distance down, and it's about the same because it reaches the same sort of final velocity. So you throw it up, it gets to the top where it stops, and then it comes back down again, and you sort of catch it.
Sir.
Yep.
Sorry for interrupting, but can you let me in from my computer?
Oh, sure. Hang on a second.
Thank you.
Go back to Zoom. Oh, okay. Abdullah, Ibrahim, Al El Mahdi, and Ali. Why were you late, you guys?
No, Mr. I'm not late, but I joined first. A second.
No problem. Can you turn off your phone then?
Mr. You do the attendance?
Okay. No problem. Right. So the reason I'm spending a bit of time on this one is because I want you to have a look at the next question. And that's this question. And I'm going to upload this to Google Classroom for you to have a look at now. And I want you to try and do question 11. And I want you to try and do question 12. I'm not giving you any hints on this one yet. I quite like the hints, the video hints. I think that's quite good as a way to start, but we'll also just try
To help us.
Sorry, what?
I said not any video to help us in this two question.
Yeah, I think I can make a video if you like.
Yeah, make a.
I will upload this question now, and you have a look at it, and then I'll record a quick video where I'm doing some hints as well. If you think the hints are quite a good thing, did you find them useful in general? The hint videos.
Yes, Mister. It help us to answer, to get the answer.
Right. Well, let me upload this. This is kind of the end of the teaching part. I want you to try these now. And anyone who didn't manage to upload their multiple choice questions, if you can do that, that would be helpful. Because I do want to, and I don't want,
Your answer not clear.
I don't want the answers, guys. I don't want you to give the answers. I know what the answers are. What I want to give, what I want to see is your sort of working out. That's what I want to see. So you're thinking behind it. So I'm going to stop this now.
Sir, your sound is not clear.
My sound is not clear. Can you hear me now?
Yes.
Can you hear me now? Is it better? Okay, so what I said is I'm going to upload to Google Classroom now the 2 questions that I want you to have a look at this lesson. And then I will, while you're having a look at that, I'll record a quick video and I'll upload that so you can see it. Okay?
Okay, Mr. Thank you.
Any questions?
Mr. Sounds good.
No, thank you, sir.
Great stuff. All right, so I will post that and I will see you, well, I'll see you officially tomorrow, but how is it working? Is it better? Because I think actually it's probably better because you can stay at home, you can go online for 5 or 10 minutes, you get set some work, then you can sleep and relax, and then in the afternoons you can get a tutor to come and help you. So I think it's much better. But I don't know what you guys think.
Mr.
Yeah.
Sir,
Yeah.
the AS will cancelled or not?
No, the AS is still going ahead. 10th of January.
Okay.
Yeah. I'm sorry about that, guys.
I feel
No,
But don't worry, you'll still get a chance to do it in the summer, even if you don't do brilliantly in the January one.
Sir, next week.
Okay. All right, dudes.
Next week we're
Okay,
online
sir.
or we come school.
Yep. All right, I'll see you guys in a bit. All right.